Okay. So hello Tharuni and Tehseen. So I hope my mic is working and you're able to hear me clearly. So let's get started in 2-3 minutes so a few others can also join the meet as well. So I guess I'll start in 2-3 minutes, like around 6-5. So yeah. So I hope my audio is clear to everyone. So if it is not, like, you can inform me via chat if there is some disturbance or anything. So today, this is, I guess, 10th session, the 10th session for the Discrete Maths NPTEL course. So just to reintroduce myself, I'm Lakshya Saggi, the Discrete Maths TA for the Tuesday sessions. So in today's session, we'll be discussing problems related to, like, the content of this week, which was mostly recursion. So we'll be discussing problems related to concept of recursion only. The binary strings and the tower of NOE and stuff like that. So I guess I'll just get started with the problems now. So let me just share my screen, guys. Okay. So I shared my screen. So is everyone able to see the Word document on your screen? Can someone let me know via thumbs up if or in chat if you guys can see the screen? So, okay, it's visible. Nice. So let's just get started with the first question then. So first question is, like, not related to recursion, it's more related to complexity. So I guess this was also a concept which was covered in these sessions, like this week's lectures. So we'll be discussing some of this also. So the question asks, which of the following statements are true complexity wise? So first of all, just to remind you guys about the definitions, maybe. So while viewing, while checking if Fn has higher, okay, sorry for this. So I'm just writing down how do you say which if a function Fn has higher complexity than a function Gn. This has been discussed in the lecture, so I'll just discuss this again in short term. So while checking if Fn has a higher complexity than Gn, uh, we just need to check how Fn and Gn behave at large values of n. Like we are not interested in smaller values of n. So in small, if it is possible that suppose like f of n has a bigger complexity than g of n, but f of n is smaller than g of n for smaller values of n. So it is completely possible. We just care while answering the question related to complexity only about the values when n is large. And this sort of makes sense more because in computer science, whenever we are solving problems, we are more interested in solving problems for larger input sizes. For smaller input sizes, it's generally easier to design algorithms and maybe we can hard code some stuff also. But when the input becomes very large, that's when the most restrictive case happens generally. So for comparing generally two functions complexity wise, we only care about checking for larger values of very high values of n. So you can just assume n tends to infinity. So we just need to check how fn and gn behave when n becomes very large, or you can say infinity. So while answering this, so also like we ignore the constant terms. So suppose like we get f of n is something like 50 times g of n, then also we'll say that f of n and g of n have same complexity. So here we also ignore the constant terms. So that is like, let's say f of n is 50 times g of n. That is, uh, maybe an example would be a better statement. So example, if f of n is 50 times g of n, still f of n and g of n have the same complexity. So this is how we view the complexity statement. So like to formalize it a little more to get you guys a better understanding of what is like complexity, I'll just tell you guys this definition also. So we know what are limits, right? What are limit when n tends to infinity and something like that. Like limit is something which we have studied in high school as well. So how you can write something like this is, so n goes to, let's say, limit n tends to infinity and fn by gn. Okay, fn by gn is infinity. So let's just say. So I'm saying when does a function f of n have higher complexity in g of n? F of n. So if a function f of n has higher complexity than a function g of n, then another function g of n, if and only if the limit of fn by gn is infinity. So, or maybe like is equals to is a bad term. So, or maybe I guess this is okay. So this is something which you should keep in mind. So I've just like italicized this as it's the formula. So suppose we are given two functions f of n and g of n, and suppose I want to calculate the and I want to say which of the following functions has a higher limit. So this is same as like the previous argument. I've just formalized it a little bit. So I want to say whether f of n has higher complexity or not. So I can just check the value of f of n by g of n when n tends to infinity. And if this comes out to infinity, then I'll say that f of n has higher complexity. Like you can say, so this just means that when n becomes infinity, basically when n becomes very large, f of n becomes infinitely larger than g of n. Not some constant times. Like here, f of n only grew 50 times g of n. But here I'm saying f of n grows infinity times g of n. So that's when we say that f of n has higher complexity. So this is sort of the intuitive definition for complexity. So if one of the function grows infinitely larger than the other function, then we say it has higher complexity. So similarly, like to check if g of n has higher complexity, then we'll just see the ratio of g of n by f of n. So basically, if this is comes out to zero, like f of n by g of n comes out to zero when limit tends to infinity, then we'll say that g of n was like of higher complexity. And if this limit comes out to constant, then we can say that they are of same complexity. Like here, f of n by g of n comes out to 50, and we said that they have the same complexity. So everything can be derived from this expression. This is the main thing which I believe you guys should know. So yeah, this is the basis for the complexity stuff. So, and this is like the definition, or you can say like, how do you see? So how FNGN become when n becomes very large. And this is a mathematical statement for this thing only. Like for this English argument, this is the mathematical form. So here n is becoming very large and we are seeing the value of Fn by Gn. So yeah. So this is how we generally, this is how I personally like to see complexity, how complexity is defined and stuff. So let's come to the question then. So question is saying which of the following are true? And I hope like limit and everyone knows how to calculate limit and tends to infinity like Fn by Gn. Since we have studied limits in high school also like and like the function Fn and Gn won't be too difficult also to answer for us generally. So yeah. So the first question is asking which of the following is true complexity wise. So let's just go option by option. So let's just see option A. So option A is saying us 500n square is less than 1500n. So for this question, do you guys think it is correct complexity wise? Because uh, you can see like basically we are interested in the highest power of n and we are not interested in the constants. So this 500n square can just be thought of as an n square and this 1500n can just be thought of as an n. For smaller values of n, for sure, for n equals to 1, this function is larger than this. But since we have to compare it complexity wise, so in terms of complexity, we just need to argue when n is very large, then which of the following values will be larger. So this function will grow as fast as n, like the highest power is n here, but this will grow as like as n square. So actually this function is growing faster. Like this function grows as fast as n square, and this grows as fast as n square is greater than n. So this will be like this is not true, as like 500 n square will have a larger complex will be of bigger size in terms of complexity than 1500n. And you can just see this using like the uh, this limit definition also. So I'll not write it down, but you can just see easily that like if f of n is 500n square and this is like g of n, then limit of 500n square upon 1500n would come out to like n by 3. And when n tends to infinity, this n by 3 will also tend to infinity. So so we can say that like 5000 and 500n square will have higher complexity than 1500n in fact. So you can, I hope my argument was clear to everyone. So I just took like the limit of Fn by Gn. So 500n square by 1500n when limit n tends to infinity will come out to like n by 3. And when n tends to infinity, it will go to infinity. So we'll say that like the numerator f of n had higher complexity than g of n. So the option A is incorrect. As n square has a higher complexity than n. So this is to see like straightforwardly that there is a coefficient of n square, we can equal constants and like n square is higher than n. So all sorts of arguments work here, like by saying about you can just argue it using limits. You can just also say directly that n square goes faster than n, and both the explanations work fine. So option B is maybe I just write this as not true, but as false. Not incorrect. Yeah. So in option B, it's saying 5000 n square is greater than n cube. So again, you can see like using similar arguments, this has a coefficient of like this has the term of ignoring these constants. This has the term n square and this has n cube. So limit of n cube by n square as n tends to infinity is n and like which is infinity. So in fact, like n, you can just see that like n cube grows faster than n square, right? It's no big deal. So this statement is also in fact false, as like n cube will be of higher value complexity wise than this n square. So this is also false. I hope what I'm saying makes sense to you guys. If it's not clear, you can just type in chat and I can maybe repeat the arguments or try to explain them in some other manner. So yeah, as so this was false as the left side term n square has lower complexity than n cubed. So now comes the option C. Option C again, it has like this side has the coefficient of n and this side has a coefficient of n square. So n square grows faster than n. Like we can just see it using limits also, like limit n square by n is equals to n. When n is to infinity, this will go to infinity. So in fact, this will grow faster. So this should have a higher value than 300n, like include the constants n. So this is also incorrect. It should be the other way around, like 3n square should be greater than 300n. So this is also false, as n square has uh, higher complexity than n. So now comes option D. So option D says 999 times n square is less than 9n cube. So here we see like this has the coefficient, this has the term of n square, this has the term of n cube. So since n cube grows faster than n square, like you can see it using limits again, like limit of n cube by n square is n, and when n tends to infinity, this goes to infinity. So in fact, this term is larger than like the n cube term is larger than n square term, and we can just ignore the constants. So this statement, in fact, is true, like since n cube has higher complexity. So this will in fact be true as n cube has higher complexity than n square. So yeah, so the final answer is option D is correct. And only option D is correct. All other options are false as we have discussed. So I'll just underline this. So yeah, 1 second guys, let me just get some water. Oh yeah. So now let's get to the second question then. If this complexity question was clear to everyone. So the second question is asking us like it's a multiple choice question, but I guess it's a very basic recursion question only. So it's asking how many n-bit binary strings are possible without having consecutive ones. So for this, so a similar sort of thing you guys must have seen in lectures also if you have seen the lectures. So uh, there, I guess, gave the example of without having consecutive zeros, and here the example is for without having consecutive ones, but the logic remains the same. So like without even getting into that, like if you've not watched the lecture for some reason. So let's just try to solve this. So this can be thought of using this statement. Uh, Hi Suguna. So I'll be sharing this doc at the end of the session. So I guess you guys must have been given a link of a Google Drive, I guess, where I upload these documents weekly. So you will be getting access to this document uh, after end of today's session, or maybe like tomorrow morning or something. So there's a Google Drive or somewhere. So I just upload this document into the Google Drive. So I'll be uploading this after this session gets over. So yeah. So like coming back to the question again. So this question can be solved using like recurrence. So how we can solve? So let's just say like, so basically we have to find how many n-bit binary strings are possible which do not have any consecutive ones. So a binary string should not, so this binary string should not contain terms like 1100 or like 01100. So two ones should not appear together. They must always be separated by a zero. So yeah. So let's just for Tn denote the uh, number of n-bit binary strings without having consecutive ones. So Tn denotes the required number which we want, the number of n-bit binary strings which do not have any consecutive ones. So let's just try to find out the basic cases, what happens like for let's say T of 1. So how many, what is the number of n-bit binary, 1-bit binary strings? So I replace n by 1. So number of 1-bit binary strings without having consecutive ones. So what would be the value of T of 1, guys? What's your answer? Yeah, yes, you are correct. So answer will be 2. So one, what are the possible 1-bit binary strings? It just can be either a 0 or a 1, since it contains 1 bit only. And both of these, this 0 as well as 1, they both of these do not contain consecutive ones. So yeah, so T of 1 will be 2. Similarly, what the value of T of 2 would be? So T of 2 would be like basically what are the possible 2-bit binary string? It is 00, 01, 10, and 11. So the 11 string will contain consecutive ones, right? So that would not be possible, but other three cases 00, 01, and 10, all of those are possible. So there are three possible cases for 2-bit binary strings which do not have consecutive ones. So T of 2 would be 3. So I've just like given these two, like T of 1, T of 2, you can define the recursive relation irrespective of finding this T of 1, T of 2. I've just given these values so that you guys can get a bit of intuition or like understanding of what the question is asking us to do. Or maybe you can consider this the base cases also. So anything works fine. So, and how to find the recurrence relation for this, like for this T of n. Suppose I want to find the recurrence relation for T of n. So how it can be done is, so let us look at the first bit of the, so now I want to find this T of n, right? The number of n-bit binary strings without having consecutive ones. So now let's look at the first bit of the n-bit string. So suppose if the string was like of length, suppose the string was something like this, A1, A2, A3, up to AN, where like A1 to AN all are like 0, 1. Oh yeah, sorry for this. All AIs are 0, 1. So n-bit string looks like this only, right? It looks like A1, A0, A1, A2, A3. Okay, I missed this. Okay, let's just keep it like this. So an n-bit string will look like A1, A2, A3 up to AN, where all AIs are 0, 1. Right. So now let us look at the first bit of this n-bit string. So that is A1. So let us look at A1. So there can be two cases. So case one is like A1, yeah, A1 is 0. And if A1 is 0, then what can we say? Like, suppose if A1 is 0, then what can we say for the possible like for A2, A3 up to AN? How many values can they take so that they do not contain any consecutive ones? So what I'm trying to do, and just to give a summary of the solution. So what I'm trying to do is I'm checking the value of, like, I have to find the possible values for this A1, A2, A3 up to AN, right? So that they do not contain consecutive ones. So I take this A1. So since this is a binary string, A1 can either be a 0 or a 1. And these two will be disjoint cases, right? A1 can't be 0 and 1 at the same time. So A1, so there are two cases that A1 is 0, and the second case would be, I'll just write the second case also here. So case 2 would be A1 is 1, and there can be no further case, right? And what will be the and we'll try to calculate the number of ways in this case and number of ways in this case, and we'll sum up these two cases as these are disjoint. So the final answer for us, the value of T of n will be the sum of these two cases. So let us look at this first case. So in first case, what happens? The value of A1 is 0. Right? So A1 can be replaced by a 0. And now we have to find number of ways of A2, A3 up to AN such that we do not contain any consecutive ones. But now basically the trick here is to see that these are n minus 1 bits. And the problem actually reduces to finding. So now the problem basically reduces to finding the number of n minus 1 bit strings which do not contain consecutive ones. As A1 was itself a 0, so it will not contribute to any consecutive ones, right? So we can just ignore this A1 part, and now this A2 up to AN part becomes an independent problem of smaller size. So this contains n minus 1 bit. So basically now what we need to find number of n minus 1 bit strings which do not have any consecutive ones. And this was only possible because A1 was 0. So it won't contribute to any consecutive ones, right? So in this case, because of these A2, A3 up to AN, we'll get basically only n minus 1 bits. So for this case, we'll have T of n minus 1 ways. And this is because like this part A2, A3 up to AN will, these are n minus 1 bits, and these values can be found out which do not contain any consecutive ones using T of n minus 1. So we're trying to use some sort of recursion here. So this is the recursion formula. So here there would be T of n minus 1 ways. And let's say case 2 is when A1 is 1. This was the case when A1 was 0. Then we found out that we need only T of n minus 1 ways. But there can be another case when A1 has a value of 1. So then what will happen? So let's just see. So A1 will be like, suppose A1 has a value of 1. And now we need to find the value of A2, A3 up to AN such that the whole string A1 to AN does not contain any consecutive ones. So now actually you can see that A2, so when A1 is 1, then A2 is also not totally free. Like if A2, initially A2 can take the value of 0 and 1, right? But if A1 takes a value of 1, then A2 can only take a value of 0. And this is because if A2 was also 1, so I'll write this down also, but I'm just explaining this part. So we are in the case when A1 is 1. So you can just remove this. You can just think of removing this A1 and instead think of it as 1. So the string is now 1, A2, A3 up to AN. And now in this string, we want number of n bit strings without consecutive ones. So now this A2 also cannot be 1, right? Because if A2 was 1, then the string will have a consecutive one, like this A1, A2 both have 1. So when A1 is 1, A2 will have to be 0. Right? So in this case, A2 will need to be 0 equals to 0 so that we don't get consecutive ones. So I hope this is clear. So now as A2 is 0, so now what the question problem statement has reduced to, so A1 is 1 and A2 is 0. And now we need to find the values for A3 up to AN such that we need to find number of n-bit binary strings. And we have already decided the values of A1 and A2. And now we need to decide the values of this n-2 remaining bits. But note that since now A2 was 0, so now A3 to AN all are free to have whatever value they want till as long as they satisfy that they do not contain any consecutive ones. Since A2 is 0, it will not contribute to any ones. So now what I can say, so as A2 was 0, so now these n-2 bits are free to have any values, and so as long as they don't contain any consecutive ones. So this will just take like t of n-2 ways, right? And this is because like A1 was 1, but A2 was 0. So now A2 will not contribute to any consecutive ones. So A3 to AN can now take any values as long as that particular string A3 to AN does not contain any consecutive ones. And this is an n-2 bit string. So it will have only like t of n-2 ways. So I hope this is clear to you guys. So I'll just underline this also, or maybe both this, sorry. So now what does this imply? Uh, What does this imply? So now the final answer for us will be like, since case 1 and case 2 are like disjoint with each other, as like A1 can only take either a value of 0 or a 1. So since both cases are disjoint, as A1 can only be either 0 or 1. So what we can say is like that the value t of n will be nothing but the sum of the number of ways of case 1 and for case 2. So we can just say that t of n will be equals to t of n minus 1. So maybe I'll just write down. So we can sum up both. We can sum the ways for both the cases to find the total possible ways. So what I'm saying is, so as both cases, case 1 and case 2 are disjoint, so we can sum the number of ways for both the cases to find the total possible ways. So what this statement says is nothing but the mathematical form is just t of n will be equals to nothing but t of n minus 1 plus t of n minus 2. So this is the recursion formula for our problem statement, the number of n-bit binary strings without consecutive ones. So this will be the formula, and the base case will be t of 1 will be 2 and t of 2 will be 3. So this is, I'll just put this also. So yeah, so final answer of what we get is like t of n is t of n minus 1 plus t of n minus 2, t of 1 is 2 and t of 2 is 3. So let's just see which option matches with this. T of n is t of n minus 1 plus t of n minus 2. Recursion is correct, but t of 1 is 1 and t of 2 is 1. So I think this is incorrect, as t of 2 we already discussed would be 3, the 0, 0, 1, 0 and 0, 1 strings, if you guys remember. So second is t of n is t of n plus t of n minus 1, which is incorrect, as we had n minus 1 plus n minus 2. D option is also incorrect. It says n minus 2 plus n minus 3. And C option says t of n is t of n minus 1 plus n minus 2. And t of 1 it says is 2. And t of 2 it says is 3. So option C is correct. So yeah. So right. So is correct. So I'll just underline the correct answer. So I hope you guys understood this. So let's just come to the next question now. So you can see recursion is actually not that hard to do when you get the feel for it or you get to it, like you understand what is happening in the questions or what are the possible ways of dividing the bigger problem into smaller problems. So once you get the hang of it, it's not too difficult to see. Maybe for beginners, it might seem a bit of a daunting task, but trust me, it's not that difficult. So yeah, similarly, like first question was also, I don't think too difficult. You just need to know the basic concept of complexity. And if you are not able to just directly see which function is greater or not, just go to this definition, which I told you, like the limit one, like take limit and tends to infinity of fn by gn. And in this manner, you can find the complexity comparisons easily. You can do the complexity comparisons easily. So yeah, again, let's just enough of philosophizing. Let's just come to the question. So third question is saying, let A and B a sequence that satisfies the recurrence relation. An is equals to 20 times an minus 1 minus 25 times an minus 2, where a0 is 4 and a1 is 14. So, and now what we need to do is maybe, okay, I think that should be this. And we need to find the values of a3 and a4. So this is the standard, like this is a standard reconciliation given to us that like an is 20 times an minus 1 minus 25 times an minus 2. And what we need to do is, yeah, so and we are given a0 and a1, and we need to find values of a3 and a4. So one way is, so one way which you might do is like you guys must have seen in the lectures how to solve this sort of reconciliation. So we just take it as x square and an minus 1 as x and an minus 2 as constant. And we say x square is 20x minus 25. And we try to find the roots of that characteristic equation and then find out the constants associated with those roots using these conditions. So method one is solve the characteristic equation. I believe you have like I'll assume that you have gone through the lectures and you already know what the characteristic equation of a recurrence is. So method would go proceed as follows. So you solve the characteristic equation of the recurrence, then find the constants C1 and like let's just not say constant C1 and C2, but find the constants using the base cases. And and now like when you have, so basically now you get the general formula for the recurrence relation. So you just like basically find out the recurrence relation, find out the roots of the recurrence relation, and then find out the constants using the base cases. So after that step, you will obtain the general formula for the above recurrence relation. So we will obtain for the above reconciliation. And now what you can do is just plug in the values like so we need to find a3 and a4. So you'll just need to plug in n equals to 3 and n equals to 4. Then just plug in n equals to 3 and n equals to 4 in the formula. So this method is okay, I guess, but I personally won't like you guys to do this because this requires a lot of solving, right? First, we need to solve the quadratic equation, then we need to find the constants, and then like you'll need to find out like the final formula which you'll obtain is will be in the form of like exponents. something like roots to the power n. So you'll need to find the cubes and the power fours of the formula, which I personally don't think you need to do all of this for this question. So this was method one. And another method is, so the trick here is to see is note that you just need to find like A3 and A4 only, which are not too far from A0 and A1. Like after, if you're given A0 and A1, you can just plug in this formula value of n equals 2. So you will get A2 is 20 times A1 minus 25 times A0, right? And you already know A0 and A1. So you'll be able to obtain A2 faster. And after obtaining A2, you have A2 and A1, you can obtain A3. And after obtaining A3, you can obtain A4 also by just plugging in these values in these formulas. So instead of solving all of these equations, so you will require, personally, I think you will require the lesser work in just plugging in the values of A0 and A1 to find A2, then find A3 from that, and then find A4 for that from that. So doing an iterative procedure instead. So since these values required like A3 and A4 are not too far away from A0 and A1, suppose you need to find like something like 8,000 or something along those lines, then I believe better method is using this method one only, since otherwise you need something like 1,000 iterations to find out the final value. Whereas using method one, you'll get the general formula and you can just leave it in like form of exponent. Like suppose we get something like 3 to the power n, you can just leave it to 3 to the power 1,000. You will not need to explicitly calculate. But in this, the iterative method, which I'm just telling you guys about, like just from A0 and A1 calculate A2, then calculate A3. In this method, you need to do explicit calculations for A2, A3, and so on. So this method works better, like the method two, which I am going to tell you guys, which I just told you orally also, like calculate A2 from A0 and A1, then calculate A3 from A2 and A1, and similarly A4 from A3 and A2. So this method works better when the terms the whose values which you need to find are closer to the base cases which have been given to you. So since A3, A4 are close, like here, like A0 and A1 and A3 has only like A1 and A3 has only a gap of one term, like so you need to calculate A2 and then you can calculate A3 easily. So since these are close in some sense, the base case and the value which we need to calculate, so the second method is probably better. So I'll recommend this. I'll just state the method also. Recommended here. So what's the second method? Just iteratively calculate the value of A2, comma, A3, comma, A4 from the given recurrence relation and the base cases. So just to do a run of this, like what I mean by all of this. So what I mean by all of this, I can just tell you guys. So we know that an equals to, so that is, okay, so Aditya has already answered in the chat that A3 is 3250 and A4 is 60,500. So I'll just check the answer also, but like it's just like after this, it's just calculations only, and calculations can be done by you guys yourself also. But yeah, Aditya, so your answer is actually correct, but I'll just explain it for others also. So, so we have been given the relation as an is, maybe I'll just copy this relation. An is 20 times an minus 1 plus minus 25 times an minus 2. So now let's just put in n equals to 2 in this formula. Putting n equals to 2, what we get is, so I'll just put n equals to 2, we'll get here an as a2, and this an minus 1 as 2 minus 1 is 1. So this will be 1, and 2 minus 2 is 0. So this will be a0. So what this implies is like we'll get A2 is 20, A1 minus 25 times A0. So I'll be getting the value of A2 as 20 times A1. So A1 is 14. So I'll be getting something like 20 times 14 minus 25 times A0, and A0 was 4. So I'll be getting something like this. So which will be equals to, so I'm calculating the value of A2 here. So this will be like 20 times 14 will be 280, and minus 25 times 4 will be 100. So this will be 280 minus 100, which will be like 180. So A2 I get as 180. Now I put in this formula n equals 3. So putting n equals 3 now. So note that why did I calculate A2? It will become clear to you guys in a minute. So when I put n equals 3, so I'll get A3 is 20 times A2 minus 25 times A1. So for calculating A3, what I needed was 20 times A2 minus 25 times A1. So I needed the value of A2 to calculate the value of A3. So that's why I earlier put n equals to 2, so that I can calculate the value of A2 first. And after that, I put n equals to 3, so that now to calculate like A3, as I need both the values of A2 and A1. So I obtained A2 earlier by putting n equals to 2. Now I can obtain A3 by putting n equals to 3. So now what we can say is, so A3 will become like 20 times 180 minus of 25 times A1, and A1 was given as 14. So now you can calculate this, and this will come out to be 3250. You do this like straightforward also, like 180 times 20 will be like 3600. And from 3600, what you're subtracting 25 times 14. And this will come out to 350, right? 25 times 14 is like 250 plus 100, which is 350. So 3600 minus 350 will be nothing but like 600 minus 350 is 250. So it will be 3250. So yeah. So now repeating this sort of step again. So now I have obtained the value of A3. Now I also need to find out the value of A4. So I'll now put the n as 4. So I'll putting n equals to 4, I'll get the recursive relation as A4 is equals to 20 times A3 minus 25 times A2. So here, like for calculating A4, I need the values of A3 and A2, which I have calculated earlier. So for A4, I'll just plug in these values. This will be like 20 times A3, and A3 is 3250. And now I'll subtract like 25 times A2. So 25 times A2, and the value of A2 was 180. So I'm not doing this calculation, and this will, you can just assume that you can just see, check afterwards of it will come out to like 60,500 or something. So yeah. So voila, we have values of A3 and A4 from the reconciliation. So yes, I'll just write the final answer also. Hence, A3 equals 3250 and A4 equals 60,500. So yeah, this is the final answer for this question. Okay, so now let's just come to the fourth question then. So the fourth question is asking uh, which of the following statements are true? And it has a bunch of statements, 3 statements A, B, C, and we need to tell which of the following statements are true. So it's also we see, so it's just something related to lectures only. So tar of NOE you guys have already seen in the lectures, and I'll assume that you guys have seen the lectures. So solution for tar of NOE comes out to be, it's just a revision based question. Solution for tar of NOE comes out to 2 raised to power n minus 1. So if you guys remember, this was the solution which actually came out for tar of NOE. So the statement A is correct. So statement A is correct. And the statement B says the recurrence relation for TRFNO is Tn is 2 times Tn minus 1 plus 1 for T1 equals 1. So this is also correct if you guys remember the recurrence for TRFNOE. And how did you find the recurrence for A? Like it was just that there are suppose we have n weights given to us. So now we'll be first offloading the first n minus 1 weights to the third stand. And then we'll take one move to move the nth weight to the second middle stand. And then we'll move back those uh, n minus 1 weights back on the second stand. So twice the work done is like 2 times the work done to move the n minus 1 weights and the one move taken for moving the nth weight. And when T1 and for moving just one weight, we'll just need one move. So T1 is 1 and Tn is 2 times Tn minus 1 plus 1. So this was also correct. And statement C is complexity of tar of NOE is n square. So the actual solution for tar of NOE is 2 raised to power n minus 1. And it says that complexity is n square. So do you guys think that 2 raised to power n minus 1 and n square have the same complexity? What do you guys think? Can you answer in chat? If someone is typing, so I'll wait for the response. Yeah. So Suguna has written that this is false. Statement 3 is false. So yeah, you are correct, Suguna, that the statement C complexity is incorrect. And why is this incorrect? Uh, so why is this incorrect? So basically, it's saying that the complexity is n square, but the actual solution is 2 raised to power n minus 1. So for these two functions, like these 2 raised to power n and n square to be of same complexity, like so basically this statement C is saying that n square and 2 raised to power n minus 1 have the same complexity. But this is not true. And why is that? You can just see it using the, like this is an exponential in n, like this grows exponentially with n, whereas this grows only polynomially with n. And like if you guys are not satisfied, so I'll just write down first and then explain it as 2 raised to the, okay, my bad, sorry. So as 2 raised to the power n minus 1 has higher complexity than n squared. And why is this the case? So again, coming back to the, if you guys like, intuitive definition was just that the 2 raised to power n function is growing exponentially with n and n square is going polynomially with n. But we can just check it using this definition also, like fn has a higher complexity than gn if and only if limit n tends to infinity, fn by gn becomes infinity. So let's just come back to that. So here fn is like, let's say 2 raised to power n minus 1 and gn is n square. So now what I'm claiming is like, let's just take this as fn and this as gn. Then fn will come out to have higher complexity than gn. And how can you say? So you'll just take the limit. So you'll take limit n tends to infinity of 2 raised to power n minus 1 upon n square. Right? I hope you guys get what I'm saying. And now since this will form like numerator is also infinity, denominator is also infinity. So infinity by infinity can be reduced using L'Hopital's rule. So we'll just differentiate both. I'm assuming that you guys know L'Hopital's rule as it has been, we do this in high school also. So we'll just differentiate both the numerator as well as denominator. So numerator differentiation, 2 raised to power n minus 1 will differentiate to like 2 raised to power n log 2. And this will come out to 2n. So again, so the numerator becomes 2 raised to power n log 2 and denominator becomes 2n. So so this is again infinity by infinity. So again differentiating. So this numerator will become 2 raised to power n log 2 whole square. Like log 2 has a square with it. I'm just doing these calculations only as these are very basic calculations. So numerator will still be something like 2 raised to power n times a log 2 square. And the denominator will reduce to 2. Like 2n will differentiate to 2. So the numerator will have a something like 2 raised to power n term, whereas denominator is a constant term. So when n tends to infinity, this will become like something like 2 raised to power infinity, which we know is infinity, right? So, and this was what we said, like if like fn by gn tends to infinity, like 2 to the power n minus 1 by n square tends to infinity at limit n tends to infinity, then we say that the fn, which was 2 raised to power n minus 1, has higher complexity than n square. So yeah, I hope you guys get what I'm saying. So suppose there was another statement. So like question, wait. So complexity of the, so let's just say there was another statement which said that complexity of the tower of NO is 2 raised to power n. So then this statement, this statement D will become correct. Because you can see that 2 raised to power n minus 1, when we take the limit of 2 raised to power n minus 1 by 2 raised to the power n, then it will come out to, so in numerator denominator you can divide by 2 raised to power n. So numerator becomes 1 minus 1 upon 2 raised to power n and denominator becomes 1. So at limit n tends to infinity, this will become 1 only. So it will not blow up to infinity. So we can say that these both will be of the same complexity. So you can just see directly as both are growing exponentially with n, with the exponent being of 2. So this will come out to be of same complexity. So yeah, so 2 raised to, so complexity of RNO is actually 2 raised to the power n and not n square. So just don't mix the base and exponent with each other. So one have the same complexity. So yeah, I hope this is clear to you guys. So then if you guys have any doubt, you can ask in chat. Otherwise, I'm moving on to the next question now. So fifth question says that so fifth question is again a complexity basis question and not too difficult. So it's just asking which of the following sequences is correct in terms of complexity. So we have been given a bunch of sequences of functions. So order log n square, order n log n, and something like this. And we need to answer which of these sequences are correct. So will anyone like to try this question out? Okay, there's a correction, I believe. Sorry. So while seeing the question, I just realized that this log n square should instead be a log n whole square. So yes, case. So case is saying option A is correct. So your answer is on the right track. The only thing which so so the question, I can edit this question right now as it's an image. So I'll just uh, write down the edit below the question. Uh, log n square should uh, instead be taken as like log n whole square. So what I'm just saying is this has like n square inside the parenthesis, but it is like this is a, I believe, a mistake, and instead it should be like log n whole square. So log of n square will just be like 2 log n, so it will be equivalent to log n only. So it won't make much sense. So it is actually log n whole squared. So this is a bit of a correction for every option. So note this correction. Instead as log n whole squared. Yeah, I guess it makes sense. So then option. Okay, so Suguna, okay, first of all, Suguna is asking us that can you please provide us some practice problems other than assignment questions and solve problems in video? So personally, I think that these much problems are sufficient for you guys. And if you still feel the need for more problems, I believe in the discussion forum, you can access the NPTEL discussion forum on your like NPTEL homepage and after logging in. And there, TS regularly keep asking questions. Like TS regularly keep asking some questions. So maybe you can attempt those questions also, like in the discussion forum, TAs ask questions and they provide the solutions one day or after one day or something like that. So you can practice those questions also. And even if even that's not enough, then I would recommend that you can take questions from the book also. Like there has been a course book also which has been recommended to you guys. So you can like practice questions from there also. So I guess this much can be from like my side. Like I can provide these much questions, and otherwise there are questions like there are a lot of sources for doing questions, like the book, the course book, and as well as the discussion forum. So yeah, I believe a lot of options are available to you. So let's come back to this question then. Uh, so in this question, like as KS said, so KS was correct that option A is correct. So I'll just go around this and maybe we can do this question orally only. It's not as it's not too difficult of a question. So option A is saying that log n should be less than this is not log n square. So case I hope you had treated this as log of n whole squared, because log of n square will just come out to like log of a raised to power b is just b log a, right? So this will be equal to 2 log n only. And in that case, like log n and 2 log n are equivalent to each other, as we ignore the constants while comparing complexities, right? So this should instead be a equality sign then, if this was like log of n squared. But if we instead take this as log of n whole squared, then we can say like log of n whole squared divided by log of n whole squared grows faster than log of n. You can just check this using limits also, that as log of n whole squared by log n will give us log n only. And at n tends to infinity, it will give us infinity. So first of all, I guess case this much is clear to you, right? So then after this, what we can say, so after this comparison is true if we treat this as log of n whole squared, then we say that log of n whole squared is less than n. And this part is also correct. You can just check this, that basically any logarithmic function grows slower than a polynomial function, like a polynomial in n. And you can again check this using uh, the limits that take this like n upon log of n whole squared and take its limit when n tends to infinity. So this will come out to like you can check this will come out to infinity using just basic high school maths. Like n upon log n whole squared will be infinity by infinity form, so you can differentiate both denominator and numerator. So it will come out to like n upon log n whole squared will become something like 1 upon 2 log n into 1 by n. So it will come out to n by log n or something. And n by log n, you can see that you can differentiate it again, or you can just see directly that n by log n will tend to infinity. So this part will also hold true. Similarly, n log n by n will become log n, and as n tends to infinity, log n will tend to infinity. So this will also hold true. And again, this n square by n log n will again become like something like n upon log n. this n and one n from here will cancel. So this will become n upon log n. And this also tends to infinity. So yeah, option A is correct. So incorrect order. I hope it's clear that this should instead be treated as log of n whole squared. And only then we will have this less than sign. So option A is correct. Let's just see what the mistake in other options are, whether more options are correct or not. So what are the mistakes or something? So we had already established that log of n is less than log of n whole squared. And we had already established that log of n whole squared is less than order n. And n is also less than n square. It is easy to see using like n square upon n will be n, which will tend to infinity, right? So, and after that, this is the last part, which says here it says that n square is less than n log n. So this part is problematic actually, guys, because what we had established earlier was in the previous part that n log n was actually less than n square, because n square upon n log n when n tends to infinity goes to infinity. So this part is not true, as n log n upon n square when n tends to infinity will go to 0. So this part is incorrect. So incorrect, as order of n square. So it's generally good if like we have identified the correct option, but it's generally good to identify why is the wrong option also wrong. So yeah, I'm just doing that. So yeah, so this is why option B was incorrect. So now comes option C. Option C says that order n is less than order n square, which we know is correct. Then it says that order n square is less than order log n, which is not correct, as like we have seen in the original order that this was the order followed. So we see that log of n whole squared was less, like log of n was less than this and this, then this. So we can just directly say that log of n was less than n square also. You can directly say this, or you can say this using limits also. Just take the limit of n square upon log n, infinity by infinity form. So this will become like differentiating above and below. This will become like 2n divided by 1 by n, which will come out to 2n square. And like, so this will come out to like infinity when n tends to infinity. So for in option C, this part that n square is less than log n is incorrect actually. So this is incorrect, as order n square is greater than order log n. So this going now I'll try to go a bit faster for the remaining two options. So I'll just say like option D in this is correct. This is again incorrect. Like option C also we had that n square was less than log n was incorrect part, and in D also will have the same part, as n square is greater than log n, and here it says n square is less than log n. So yeah. Now let's just go to option E. Option E says that this is log of n whole squared is less than n log n, which will be correct, as can be seen from earlier. And this will be less than log n is incorrect part. N log n will be greater than log n, because when we take the ratio of n log n by log n, it will come out to n only, which will tend to infinity when n tends to infinity. This is incorrect, as order n log n is greater than order log n. So I hope this makes sense, guys. I'll just write down the final answer. So only option A is correct. Hence, option A is correct. Right. So let's just go to the sixth question then. Okay, so sixth question was given the sequence 0, 1, 1, 2, 3, 5, 8, 13, and so on. What is the 23rd term in this sequence? So this is what the question is asking. So first of all, to find the 23rd term, we need to first of all identify the sequence also, right? What is the sequence for which we need to find, since 23rd term has not been explicitly given to us? So this sequence 0, 1, 1, 2, 3, 5, 8, 13. What is this sequence, guys? You guys, like, you guys should be able to answer this if you have gone through the lectures. So what is this sequence? Okay, nice. So Aditya is saying that this is Fibonacci sequence. So yeah, you're correct, Aditya. So the above sequence is the Fibonacci sequence, and Fibonacci sequence follows the expression, the recursion that t of n is t of n minus 1 plus t of n minus 2. So basically, one term in the sequence can be obtained by summing of the previous two terms. So 8 is just some 5 plus 3. Similarly, 13 is just 8 plus 5. And similarly, next term will be 13 plus 8, which will be 21. And similarly, next term will be 21 plus 13, which will be 34. And like so on. So it's easy to see like what is the Fibonacci sequence. So it's like this is the Fibonacci sequence. So again, we just need to find the 23rd term of the Fibonacci sequence. And we already know the recursion also. And we already like to finding this 23rd term. You guys must remember, let's come to a previous question again. So here in third question, we had to find like there was given a recursion relation and we had to find like third and fourth term. And for this, we mentioned two methods. Like method one was like solving characteristic equation and obtaining general formula, and then like plugging in values n equals 3 and n equals 4. So I guess in lectures, we have already derived the general formula for Fibonacci sequence, which is something like 1 upon root 5 times 1 plus root 5 by 2 raised to the power n minus 1 by root 5 times 1 minus root 5 by 2 raised to the power n or something like that. So in that formula, you can just plug in n equals 23. So you need to calculate something exponentiate to 23, which you can do it. I think it's like wastage of your time. So a better method, like I recommended here also, just iteratively calculate the values of A2, A3, A4. And so here, like you'll need to calculate, like this will also involve something like 20 or such steps, but it will, I believe, reduce the number of multiplications required. So you'll need to calculate in the Fibonacci sequence. So sorry again. So similar to this iterative method, you'll need to just calculate like this was the 0th term, this was the first term, second term, third term, fourth term, fifth term, sixth term, seventh term. Then you'll calculate eighth term using these seventh and sixth terms. Then you'll calculate ninth term using eighth and seventh terms. Then 10th term, 11th term, 12th term. So it will be around like you need to do 10 or 15 additions. And after that, you will be able to find the 23rd term. I'll not do these calculations for you, as similar question has already been discussed in the third question. So I'll just give you the answer. So I just mentioned can be done either using iterative method, which I discussed earlier, or using the general formula for Fibonacci sequence. So both methods can work. It's up to you what you find more comfortable. I personally find the iterative method more easier to do since it involves only additions and not multiplications. So I'll just write down the answer. Answer will come out to, so I haven't done this myself, but the answer comes out to 28657, I believe. So yeah, I'll just underline this so in case you need practice. So yeah, yes, case the answer will be this only 1 by root 5, 1 plus root 5 by 2 raised to power 23 and minus 1 by root 5, 1 minus root 5 by 2 raised to power 23. So I will just plug in the value n equals 23. So yeah, I'll just maybe if someone asks you explicitly what is the exact integer value, so you need to expand this also, right? So it will become a lot of hectic work. If someone asks you to expand this, it's better to do this using the iterative method. Like I personally find it better to expand using the iterative method, and the answer will come out to like something like 28657. So yeah, not too difficult of a task. So now let's come to the seventh question. The seventh question is saying to us that Paras is reading a novel that consists of some n pages. Right, so n is some variable. So novel consists of n pages. And while he reads the book, his dad calls him for some work. Being in a hurry, he forgets to put the bookmark on the page he was reading, though he remembers the page number. So, how much effort will Paras require to get back to the page that he last visited? So suppose like book was something of like 10,000 pages, and Paras remembers that he was on page like let's say 2057. So in how many steps, how many effort, or let's just say steps, will Paras require to get back to the page he last visited? So he only knows the page number of he only knows the page number which he needs to open. But like suppose even if I knew like I need to open page number 507. So I'm not guaranteed, right, that the page which I'll open just exactly will be the page 507, right? It can come out to something like 700, 800, or something like that. So if I want to do this, like, so how many maximum, like if I want to do this smartly so that I minimize my effort, like how many maximum steps will I be taking? So any guesses? This sort of concept you have also done in your lectures. So if you've seen the lectures, I think you might be able to answer this. So, any guesses, guys? KS or Aditya or Hital? So just think of the question as we are given n pages and we need to exactly arrive at some page number. So how much effort will I need to put in to arrive at that page number? Okay, so maybe like it's the concept you have done in the lectures, but maybe it's not too easy to see. So login steps will be needed. And like first of all, what are different techniques by which Paras can go to page the required page number? He can just open every page at a time. He goes to first page. Let's suppose I want to go to like 6,000 page. So what I can do is I just open first page, then I go to the second page, then I go to third page by flipping the page, then I go to fourth page. So I'll take like 6,000 steps, right? I'll need to flip 6,000 pages to get to 6,000 page. So going to n pages can take using this method like n steps. Suppose I want to go to nth page. One way is to do this is I go to the first page, then flip to the second page, then flip to the third page, and so on. But another smart method which we had discussed in which was discussed in the lectures was the binary search, right? So yeah, KS you have written in the chart T of n by 2 plus 1. So yeah, you are correct. This is basically nothing but binary search, right? You have something and add 1 to it. This is the concept of binary search. So what Paras can do to go to the correct page number is he'll just take his book and suppose he wants to go to some page number, he'll just open the he'll just open the middle page of the book. Like middle page you can approximately open in a book, right? It's not too difficult to like just like exact middle or it's also not needed. Approximate, you just need an approximate middle, right? So you just take approximately the middle of the book and open that page. And if you see that page number is greater than the page number which you actually require, then you just take the remaining portion of the book and again open its middle and see whether that is what you require or if the page number which you require is greater than that. And like you can proceed as follows, right? So every time you do this, every time you open something, every time you open a middle page of the remaining pages, then your problem gets halved, right? Either you discard one half of the pages and accept the other half. So that's something like T of n is T of n by 2 plus 1, which is nothing but binary search. I hope you guys understand what I'm saying, right? This can be thought of as a binary search problem. as we can somewhat open the middle page of the book approximately. Always open the middle page of the so I hope you guys see what I'm trying to say. So login steps should be needed. This can be thought of as a binary search problem where I specifically want to go to the page number which I had remembered. So we can always somewhat open the middle page of the book and we go to the middle page and we see if this is the page which we require of the or the page required is on the right side of this page. So we discard the left side fully and we go to the right and we go to the middle of the right side. And then we again check if this is greater or lesser. And so this in this way, we can halve the number of pages every step. And so this way we'll need log n steps at most. So I hope it is clear to you guys. So the important property used here was that the pages are ordered, pages are numbered, right? So first page will always come before second page and second one page will just be immediately before third page and which will be immediately before fourth page. So binary search in general can be applied to any set of items which can be indexed and properly ordered, right? So here you could have easily like this here there was a complete ordering existing like 1, 2, 3, 4, 5. That's why you were able to apply page number 1, page number 2, page number 3. So that's why you were able to apply binary search. So suppose if the instead there is a book which has page number 3 before page number 2 and page like let's say page number 5 comes after page number 2, then comes page number 4, like the order is a bit wonky. So in that case, you can't do binary search, right? Because whenever you arrive at a middle point, you can't say whether the required page number is on the right or the left because the pages are numbered randomly. So you can't just select one of those like left side. You can't just discard right side or left side yourself, right? So login steps will be needed. So I hope this is clear. So now just a bit adding a bit trick to it, not too difficult, but so suppose Paras forgets to put the bookmark on the page, right? So how does the answer change if Paras had put a bookmark on the required page? So how much effort will Paras need to do if he had indeed put a bookmark on the required page and then went to help out his dad? This is a very straightforward question. I hope like you guys should be able to answer this. Like, maybe you can type out in chat. It's not too difficult of a question. So like, suppose like the whole issue occurred because Paras had remembered only the page number but had forget to put a bookmark. So if he had put a bookmark, yes, so KS is answering one. So yeah, KS, that's the correct answer. So yeah, it was not even it was like a straightforward question. So answer is one step. And this is because like Paras can just open the bookmark page directly. So yeah, nothing fancy. The answer is one. Good job. So this is Chen. So now let's go to the eighth question. So eighth question says that which of the following is the correct recurrence relation for climbing 20 stairs? Climbing stairs simply means walking on stairs, covering one stair step in one time. So this is something you guys have seen in lectures. So uh, let's just say T of n is number of ways of climbing n stairs. Then we know that T of n is equals to T of n minus 1 plus T of n minus 2, right? So I hope you guys remember this from lecture. So climbing stairs simply means walking on stairs, covering either one step, covering either one stair or two stairs at one time, right? We are covering either one or two stairs in one step. So in one step, I can only walk like cover one stair, or I can cover two stairs. So in that case, the recurrence relation for climbing n stair becomes like tn minus 1 plus tn minus 2. And like this has already been discussed, but I'll just like discuss it early again. So why does this occur? Because like the first step I can like for climbing the next stair, I'm at the bottommost stair. So first of all, I can either take a one step, or either climb one stair, or I can climb two stairs in first step, right? So these are two disjoint cases, as these are only two possible cases. So when I take one step, then I need to climb n minus one more steps. So if I take cover one stair, then I need to cover n minus one more stairs using this one, using these types of ways only. And if I cover two steps, then I need to cover the remaining n minus two stair. So that's how this recursion comes to fruition, that T of n is T of n minus 1 plus T of n minus 2. So yeah, so I'll just write down that discuss in the lectures. And this is not too difficult to see. Also, we just discussed this orally. So like here I have written T of n, it's just written as A of n instead. So T of 20 will be nothing but, so T of 20 will be just putting n equals 20, T of 19, plus T of 80. Right. So hence T of 20 is T of 19 plus T of 18. So A20 is equals to A18 plus A19. So yeah, they have written it opposite way, was A18 plus A, but A18 plus A19 is just 19 plus A18, right? So option D is correct. Hence, option D is correct. So I have not went to the logic for, I have not written down the logic for this recursion because this has been discussed in lectures, and I just discussed this already also. So I hope it's clear to you guys. So yeah. Okay, so maybe I'll go to this question. So, okay, maybe I'll just put the ninth question on next page only. So ninth question seems like we have been given a bunch of functions, f1 and f2 and f3 and f4, and now what can, so basically we need to find which of the following statements are true, right? So our statement A, statement B, statement C, and statement D. So let's just see all of these statements individually. Statement A, what does the statement A say? F3n is an order n function. So what is F3n? F3n is 23n square plus 20 times n. So is this an order n function, guys? So I hope you are capable of answering the question now. I have discussed like the limits, and I have discussed 2-3 questions related to this. So is the function 23n square plus 20n an order n function? Can you guys answer in chat? Aditya, Hital, or Face, any of you? Is this statement correct? Yeah. So case we have written no. So yeah, it is actually incorrect. And why is that? You can just see that limit of this contains term n square and this contains n only. So limit of n square by n will go to infinity as n tends to infinity. So it is not an order n function, but instead an order n square function. So incorrect as um, n square is greater than n. Maybe I just write down this one. So yeah. So let's just come to question B, statement B. Statement B says F2n grows faster than F1n. So F2n is 50n square and F1n is 40n cube. So ignoring the constants, this is just n square and this is n cube. And it's saying F2n grows faster. So does n square grow faster than n? It's just saying option B is just saying so F2n is just n square and F1n is just n cube. So it says n square grows faster than n cube. So this statement is also incorrect. So yeah, Aditya, option B is also incorrect. So this is because like n cube is greater than n square. Right. Similarly, let's just go to statement C. And statement C says f4n is an order n cube function. So f4n is nothing but 18n cube plus 5n square plus n. So yeah, the highest exponent here is n cube only. So yeah, it is indeed an n cube function. Correct. As f, sorry, f3 of n has highest power as n cube. So f3 of n, okay, f4 of n, sorry. So f4 of n has like the highest power as n cube only. So at n tends to infinity, this will dictate the growth for f4n. So like maybe you can just take the limits also. So f4n, the limit of f4n by n cube will just come out to be a constant. And whenever limit comes out to be a constant, then we say that they both grow as fast as each other. So yeah, so f4n is an order n cube function. So statement D. Okay, why is this wrong? Statement D is saying F2n and F3n grow slower than F1n. So F1n is basically n cube function. F2n is n square function. Like the highest power is n square. F3n is also an n square function. So it's saying both these functions, both are n squared functions, grow slower than n cube function. So yeah, this is also correct. This is because like and F2n and F3n both have highest power as n square only. So we can ignore lower powers and we can ignore constants also. So it's just n square and this F3n is also n square only. And n square is like less than n cube. It grows lower than n cube. F1n has n cube. We can ignore the constant. So yeah. So statement D is also correct. So the correct answer then would be hence statements C and D are correct. So this is the answer. Let me just get some water. Yeah, so let's just go to the next question then. So next question is asking us. So I think 10th question will be last question for the day. Maybe because like I was planning on discussing another question, but it actually like the 11th question involves a concept which has not been covered in lectures. So I think I should not discuss this because I'll just be deleting this question. So because like covering something which has not been covered in lectures also is a bit tricky. I'll have to explain you guys the concepts, and like I don't think we will have that much time. So that's why we'll keep this 10th question as the last question for the day. So let's just come to this question. So it's also not a this 10th question is also not a very like concept based question, more of a calculation based question, because we have covered this concept in class and like it's more of a revision question. So let's just come to this. So 10th question is asking us, what is the solution of the recurrence relation? An is equals to 3 times an minus 1 minus 10 times an minus 2. And we are given that a0 is 1 and a1 is 2. So this is asking nothing but so let me just go back a little. So it's just asking us to solve the reconciliation and find the general formula similar to like here in the third question. What we said was like uh, we had this reconciliation and we are given base cases. So one method which I told you how to find A3 and A4 is just solve the characteristic equation, then find the constants and obtain the general formula. And this is what the 10th question is also asking us, that we just find the general formula for the reconciliation given in the 10th question. So we'll just be doing these steps only. This is just sort of a revision for your concepts in this 10th question. To find any solve any reconciliation of this form, where like an is something constant times an minus 1 plus another constant times an minus 2 plus another constant times an minus 3 and so on. What we do is just find the characteristic equation of the recurrence, then find the constants using the base cases. And this helps us find the general formula. So this is the recipe which we'll be using here. So to find the characteristic equation in this recurrence, characteristic equation is nothing but you just replace the an term by x square, an minus 1 terms by x, and an minus 2 by a 1. And this is characteristic equation of a recurrence is that only. So here the okay, maybe I'll just write that also for a revision. To obtain the characteristic equation of the recurrent, just replace an okay, sorry, an by x squared, an minus 1 by x, and an minus 2 by 1. So this is nothing. We just we just find the characteristic equation and we do this only. So characteristic equation here will be like an will become x square. So x square is 3 times x minus 10. So it's the characteristic equation is, let's just write down this here. X square is equals to 3x minus of 10. I hope you guys see how I did there. An minus 2 is replaced by 1, an minus 1 by x, and an by x squared. This x is 1. So yeah. So this is the characteristic equation. So we'll now need to solve this characteristic equation. So first of all, what we do in the reconciliation, we just obtain the characteristic equation and then solve this to obtain the roots of this equation. So this is a quadratic equation. So x square is 3x minus 10. So what will be the roots for this equation? So we can just apply the quadratic formula. So it will be something like 3 plus minus of whole square of 49 by 2. So it will be 3 plus minus of 7 by 2. So the roots will be something like, I believe, 5. Would it be 5? Maybe have I done something wrong here? Okay, so So I think I've done a bit of a calculation. There's a typo here. So this should be, I guess, a plus 10. Yeah. So sorry guys. So the recursion relation is an is 3 and an minus 1 plus 10 times an minus 2, not minus 10. To obtain a nicer. Like you could have solved for minus of 10 also, but there you would have obtained a much weirder expressions. Here the terms will be much more nicer. So that's how I set the question for this. So so x square is 3x plus 10. So in that case, what so just applying the quadratic formula, what we'll get is x, one possible value for x will get 5, and the other root we'll be getting is uh, minus minus of 2, right? So you can just check that these two will indeed be the roots. And why will these be the roots? Maybe I just italicize them. So you can just check that putting x equals 5, we'll get like 5 square is 25, which is 3 times 5 plus 10 is 25. And minus 2 will be just minus 2 times whole square will be 4. And this side will be 3 times minus 2, which will be minus 6 plus 10, which will again come out to 4. So yeah, you can see that 5 and minus 2 are the roots here. So the general term an will be written as, so as we have discussed in, as you guys have seen in the lectures also. So an will be nothing but like a constant c1 times the root 1 raised to power n, 5 c1 times 5 raised to the power n plus the other root plus c2 times, basically linear combination of two roots raised to the power n, right? So this times this. So A1 will be C1 raised 5 raised to the power n plus C2 times minus 2 raised to the power n. I hope this is clear to you guys. This is how you write the final solution, basically linear combination of the two roots. So this is the value of an. So now we still don't know the value of these constants C1 and C2. And now how do we find these constants? We find these constants using the base cases, if you guys remember. So we are given that A0 is 1 and A1 is 2. So you will put, so basically we are given the value of A0. So we are given when n equals 0. So putting n equals to 0, what we'll get is A0. Putting n equals to 0 will give us A0 equals C1 times, maybe I'll just copy this. So this will give us C1 times 5 to the power n, where n is now 0. And similarly, C2 times minus to the power n, here also n is 0. So this will be nothing but so this will be, so this equation will further evolve. So this is something like A0 is C1 times 5 raised to the power 0 plus C2 times minus 2 raised to the power 0. So now we know the value of A0. We know that A0 is given as 1. So we'll get the equation as 1 is equals to C1 times 5 raised to the power 0 will be 1. So C1 times 5 raised to the power C1 times 1 will be C1 only. This will be 1 C1 plus, and C2 times minus 2 raised to the power 0. This will also be 1. So we'll just have C2 left. So we'll get C1 plus C2 is 1. So this is the equation. Let us like maybe bold this and yeah. So this was the first equation which we obtained. And similarly, putting n equals to 1. And why do we put n equals to 1? Because we have been given like the value of A0 and we have been given A1. So instead, suppose we had been given A2 instead, A2 is 2. So I would instead put n equals to 2 and find the value. So here now, earlier, like right now, what will happen is I'll write A1 is C1 5 raised to the power. Maybe I'll just copy this and I'll write C1 5 raised to the power 1 plus minus 2 plus C2 times minus 2 raised to the power 1. Suppose instead I was given the value of A2 as something. So I would have put like here A2 is equal to C1 times 5 square plus C2 times minus 2 whole square. And from that I would have obtained. So it's not necessary to be given like A0 and A1 explicitly. You just need any two values, right? You might be given like A1000 and A2000, and still you can calculate the values of C1 and C2. And why is that? Because like these are C1 and C2 are two variables, so they just need two equations. So those two equations can be anything. They do not need to be like for A0 and A1 only. They can be for like form using n equals 1000 and n equals 2000 also. So you just need two values. It need not be that those two values be consecutive or like 0 and 1 only. I hope you guys get my point. So it's a very important point to notice because some people sometimes get confused that we must be given like A0, A1 only because what can we do without base cases? But the beautiful part of recursion is you don't even need base cases. You just need any two cases, like any two instances, like A100 and A150 will also suffice. And yeah, so that's what I meant by uh, not necessarily needing A0 and A1. So I hope you get the point. So right now we have been given A0 and A1. So this will give us A1 is C1 times 5 raised to power 1 plus C2 times minus 2 raised to the power 1. So this will give us the equation. We have been given A1 as 2. So this will give us 2 is equals to 5C1. And this will be minus 2 raised to power 1 will be minus 2. So this will be minus 2C2. So this is the second equation which we obtained. So note that we now need to solve this equation, these two equations to obtain the value of C1 and C2. So I'll try to do this orally and like write down. So this equation will be like 2 is equals to 2C1 plus 2C2, and we'll add these two equations. So we get 4 equals to 7C1. So we'll get solving the above equations. We get C1 equals 4 by 7, if I calculate correctly. And C2 equals 3 by 7. Because we can put also. So we'll get like C1 as 4 by 7 and C2 as 3 by 7. Just to verify, 4 by 7 plus 3 by 7 gives 1. And like 5 times C1 is 4 by 7. So this will give me 20 by 7 minus of 2 times 3 by 7. This will give me 6 by 7. So 20 minus 6 whole divided by 7, which will be 14 by 7, which will be 2 only. So yeah, these two equations are satisfied. So I'll get C1 as 4 by 7 and C2 as 3 by 7. These are correct. So just putting in these values of C1 and C2, putting values of C1 and C2, we get that AN. So AN I had earlier written as C1 times 5 raised to the power n and C2 times minus 2 raised to the power n. So I'll just copy C1 to be 4 by 7 and C2 to be like 3 by 7. So note that these are the coefficients. So 4 by 7 times 5 raised to the power n. And this is 3 by 7 times minus 2 raised to the power n. So yeah, KS you have also written in chat the answer is 4 by 7 5 to the power n plus 3 by 7 minus 2 raised to the power n. So yeah, your answer is correct. So this is the final answer, guys. I'll just underline this also. Okay, underlining it is bad as it makes. So yeah. So this is our final answer. And I'll not underline this because underlining this also makes exponent underline, which can cause confusion. Hence, solved. Yeah, I guess this suffices. Yeah. So the solution we get is 4 by 7 times 5 raised to the power n plus 3 by 7 times minus 2 raised to the power n. So it's like suppose if someone asks you now to calculate the 23rd term for this reconciliation, you can do that using iterative method again, which I mentioned earlier, like calculate A2, A3, A4 up to A23, or you can just plug in 23 here. So if you need to find the value explicitly, the integer value, you need to calculate 5 to the power 23 and minus 2 to the power 23. But yeah, that is also one method which you can do at least. So I hope so. This was the last question for the day, guys. As I said, like the 11th question, which I had also planned earlier, I removed it because I don't think covering something which has not been covered in lectures is a good idea. So yeah, so this was all I had planned for today. So if you guys have any doubts related to today's session or in general, we still have like 8 minutes left, so you can ask me in chat any doubts if you have. So otherwise, I guess we are done for the day and we can close the session. So if you have any doubts, please let me know in chat. I'll wait for 2 minutes, and if no one writes anything, then I'll assume that no one has anything. So if you don't have any doubts, you can also leave the session, and like I guess thanks for joining the session, and I hope I'll see you guys next week, like same timing Tuesday, 6 to 8 p.m. again. So yeah. Okay. Thanks for attending, guys. So I think no one has any doubts left. So I'll just stop the recording and maybe we can stop the close the session as well. So, so we'll meet you guys next week. So goodbye, guys. Thanks for joining.